Okay, here's some homework questions. Now remember, when you make your hypotheses, it's going to be with a parameter, not with your sample data. So, in other words, what we should do is we should probably cross off letter B right away, because that's using the sample data. Okay, and let's see. We always use an equal sign when we use our null hypothesis, so that gets rid of letter C. So here we are. Basically, we have these three options. Mice are going to go faster, mice are going to go slower, or there's just some sort of a change, faster or slower. Anyway, we think they're going to go faster, so that is choice D. The null hypothesis is it stays the same. Remember, that's no change, versus we get faster, which is our alternative hypothesis. There we go. Okay, p-values. Here we go. P-value is 0.031. And what that means is whatever our value was for our sample data, it would only happen 3% of the time. Not very likely. That's what a p-value tells us. So we're going to reject this because it's less than the alpha level right here, B. Reject the null hypothesis at an alpha level of 0.05 significance level, letter B, because it's not very likely. 5% or more, we would fail to reject. There you go. That's that one. Let's go to the next one. Okay, on this one, let's see. You know, a larger sample gives us better data. So we're probably going to get rid of the ones that say small sample. Right there. And so now we have to decide, we want to kind of reject the null hypothesis in favor of our alternative hypothesis, which is people live longer, okay? Because we would probably say that the null hypothesis would be that there's no change. Okay, and we have a better chance of rejecting the null hypothesis at a 5% significance level versus a 1% significance level. Okay, so there we go. We would kind of like to reject the null hypothesis, so this is going to give us a better chance. And a larger random sample gives us better data. There you go. Next. Okay, like I said, they are going to give you a lot of information when it comes to the power. So they tell you what the power is. And we just have to remember that the probability of making a type 2 error is, well, the probability, I'll just put this, probability of a type 2 error is 1 minus the power. Okay? So the power was 90%. 1 minus the power, so 1 minus 0.9 is 10%. We have a 10% chance of making a type 2 error. There is that one. Let's go to the next one. Okay, I'm just going to do a quick overview on this problem. Here we go. So the null hypothesis is going to be that there's no change. Here we go. Null hypothesis is that the proportion of people that feel that the satisfaction with the parking is going to remain at 37%. And then the alternative hypothesis is that the proportion is going to be much higher as far as people that are satisfied. It's going to be more people. Because they said, what was it? That the change was effective. Okay, so there's that. And we have to go through what? Random, normal, and independent. So hopefully you know about that. If you don't know about that, you have to ask me during class and say, I am not sure how to do that. I would be happy to talk about that. Anyway, let's go on. So what we're going to do is we're going to do a 1 proportion z-test. Okay. So that's what we're going to do. Now, let's see. Simple random sample of 200 students, 83. So they approve the new parking. So that's going to be our p hat. is going to be 83 out of 200, and that's going to be 0.415. Now that's the real question, is that proportion big enough to when we compare it to 37%, is that big enough to say that yes, we're improving? Okay. So here we are back with our old familiar z-score. This was p hat, and this is the parameter for the population. Here's our standard deviation, the parameter -1, divided by how many in our sample, square root. And let's see, what is that? So that's our z-score. And we want to see if we are 1.32 standard deviations above the middle, how much of the graph is left over, meaning normal CDF. So if we use normal CDF with this, we want to see, since it's bigger, we want to take that away, our normal CDF, and subtract it from 1, and we should get 0.0934. 0.0934. What is that? That is our p-value. Our p-value. The probability that this has happened merely by chance. Now there's a 9% chance that that might happen, which means we are going to fail to reject the null hypothesis. So we can't say that there was any positive change at all. Okay, there you go. Okay, type 1 and type 2 error, and we're going to talk about that parking problem. So a type 1 error would be when we're in here, meaning we reject the null hypothesis in favor of the alternative hypothesis, but the null hypothesis is still true. What are the consequences of that? Well, basically what you're saying is you think you're getting better, but you're not. So perhaps you stop trying to improve, and things really just don't get better, and you ignore the problem and move on. Now, type 2 error is when we are here, and we're saying, well, I don't think we got any better, but actually we did. So that's a type 2 error. So not knowing that you're getting better means that you might even do more things to try to improve the parking, even though the parking is getting better already. So, I don't know, a consequence could be you're focusing so much time on this parking problem, even though you fixed it, that you could spend time on other things, and you might be really annoying people with this parking issue. Okay, let's look at letter B. Okay, so what this means is, let's see, letter B. So the way we say this is that against an alternative value of 45%, we still have a 75% chance of correctly rejecting the null hypothesis. That's what the power means. So it's the sensitivity of the test. Even though it's at 45, we still reject the null hypothesis. And we have a 75% chance of doing that. And how do we increase the power of a test? Well, we could increase the sample size, or we could increase the significance level. Those are two ways to increase the power. Okay, so that's something you might just want to write down if we haven't already. There you go. All of our information is about firstborn children, so that's all we can make an inference about. That's it. Okay, because that's all we're really talking about. Let's look at letter B. So on this one, we're going to make our null hypothesis going to be, the proportion should be 50%, and then our alternative hypothesis should be bigger than 50%. Again, we are going to do random, normal, and independent for this thing. Now let's do the math. So here we are. Here is our sample statistic. I just divided this number by this number. Got that. 0.5 is what our parameter is. Here's our new standard deviation. And when you do that, you should come out with, it's a pretty big z-score, so it's going to be 5.5. Whoops, 5.5. 5.5. Which means our p-value is going to be pretty close to 0. Okay. So what do we do with that? Well, we're going to reject the null hypothesis in favor of the alternative hypothesis, and we're going to conclude that, yes, it appears that firstborn children have a much higher probability of being boys than girls. There you go.